Hello, hello, hello. In this brief worked example, we're going to be talking about the polarization operator. What is the polarization operator? Well, it's something that Beck introduces in chapter 5 and uses in chapter 8. And since you're reading chapter 8, it's useful to know what he's talking about when he refers to the polarization operator. And the best way, I think, to explain what the polarization operator is to have you recall something that you've previously studied, the spin operators that Griffiths introduced in chapter 4 of his textbook. And we'll see that the polarization operator is really something quite analogous to these spin operators. So what were the spin operators? Okay, so here's how it worked. When you have a spin one half particle like an electron, the spin state can be uh, written down as a linear combination of the spin up state, chi sub plus, and the spin down state, chi sub minus. And these chi plus and chi minus states are eigenstates of the spin operator S sub z. So when S sub z acts on chi plus, you get plus 1/2 h bar over 2. And when SZ acts on chi minus, the corresponding eigenvalue is minus h bar over 2. And the physical meaning of this is that if you measure the spin angular momentum, the component of the spin angular momentum along the z direction, and the electron is in the chi plus state, that means that you're going to measure a value of plus h bar over 2 for the z component of the spin angular momentum. And if the electron spin state is the chi minus state, and you measure S sub z, you're going to get minus h bar over 2 as a result. Okay, so when you deal with photons, you have something very analogous. We can talk about the polarization state of a photon, and we can describe sort of the standard basis that we use as the horizontal and vertical basis, and we can describe the polarization state of a photon as a linear combination of the horizontal state and the vertical state. Well, then it's entirely natural to do something completely analogous to the spin operator S sub z and define a polarization operator, which Beck uses this funny symbol. I don't know if that's a script rho or whatever. It's some kind of P there. Let's call it script P is the polarization operator. And when the polarization operator acts on a photon in the horizontal state, that's an eigenstate. So you get some eigenvalue times the state. And then it's a little bit questionable as to what the eigenvalue is going to be. In the case of spin, you're measuring a quantity with units. Angular momentum has units of h bar, and the same units as h bar, and the quantity that you measure has physical units associated with it. In the case of polarization, it's more of a direction, so it's a sort of a dimensionless quantity. So we're free to really choose these eigenvalues to be anything that you want, and it's a dimensionless quantity, and it's convenient, it turns out, to choose the eigenvalue associated with the H state as +1 and the eigenvalue associated with the V state as -1. And that's what Beck does. And you're going to see this polarization operator appear when you read chapter 8. So I thought it was important to mention it. We're not going to actually make use of it very much this term, but it's important to have at least seen it. So that's it for this worked example on the polarization operator. Hope to see you again soon. Bye bye.